I want to turn it over now to Ben Hilburn, who's been working with Edis Research for a number of years. A lot of experience and understanding of the software radio world. So he's going to talk about building software radios.
All right, how's this? Good? Yes, thumbs up. Awesome. Okay, so my goal here is I'm going to try to sort of tune the content of the talk to the experience levels of the audience. So as we go, I'm going to take a few polls and see what people know and what they don't know. And, I'll go into depth, more depth or less depth as needed. And that this should be mostly informal. So if you guys have questions mid-talk or forgetting a question, please raise your hand or something. So my name is Ben Hilburn. I manage R&D at Edis Research. And actually we can, I'll say the introduction to Edis Research for a couple slides. So I'm going to briefly kind of go over what Edis Research is and use that as a background to talk about some of the use cases, some example use cases for SDR. And the majority of the talk is that middle section there, technology behind SDR. And that's where I'll spend most of the time and really talk about the computational components and technology that made SDR possible from where we started out and where we are today. And then at the end, talk a little bit about what's coming up in the future and what's driving hardware and software requirements. So a quick introduction to Edis Research. Can I get a show of hands, people who have heard of Edis Research before? Awesome. Okay, most of the audience. Very cool. How about a show of hands for people who ever use the USRP? Okay, so a little less, but still most hands. Okay, so this is probably just a rehash for most of you. So we're our namesake, founded by Matt Edis. We're the maker, creator of the USRP, Universal Software Radio Peripheral. The key there, peripheral, is a little bit of a misnomer at this point, is we have non-peripheral products. But the USRP is a core facet, so it remains. We heavily support the Bean Radio project. Actually, most of our R&D team we hired out of the Bean Radio community, and we'll continue to be very heavily involved. So, founded in 2004, we were acquired by National Instruments almost 6 years ago in early 2010, and now we're located in Santa Clara, California. So, what do we provide? And the green is what we provide. So actually, that's not entirely true because our economics is ours as well. Anyways, so we obviously make and sell hardware, and then we provide the driver layer and now our economics as well that allow you to actually make something useful, make a really cool software radio. So there's a lot of application frameworks that you can use to build software radios, whether that's writing your own C++ and Python interfacing directly with whatever drivers provided by your hardware, or going through something like Bean Radio, MathWorks, Simulink, MATLAB, LabVIEW, or if not, I'll talk briefly. Actually, can I show hands to people who've heard of RFNOT before? Ooh, okay, all right. And then our driver, UHD, user hardware driver, talks through the OS and into the hardware. The hardware is obviously OS. So real quickly, at a high level, this is sort of our current device family. We have our low cost, this is our low cost unit. Sells for the one on the left from makes use of the 8090-61 chip, which is on our booth as well as ADI's booth in the back. All the way up to deployable embedded stuff. That's the non-peripheral device that I mentioned earlier. The general purpose M200, which has been out for a few years, and then our high performance box, which is up to 160 megahertz of bandwidth. And I'm not going to delve too much into our product offerings in this talk because Matt Edis is going to be giving a talk either tomorrow or Wednesday. I think it's tomorrow, yeah. And I'm sure he's going to provide a lot more color into what we're currently offering. But what I wanted to communicate with this slide, and it'll make sense later, is we try to service a lot of different application areas of SDR. from sort of a low-cost prototyping bus-powered device all the way up to 160 megahertz instantaneous bandwidth, high performance, fantastic RF sort of device. So going through some of the use cases for SDR, and these are I sort of picked ones out that are relatively new. I feel like most people are familiar with a lot of more common ones. We heard some really awesome ones earlier from Paul, for example, radio astronomy and that sort of thing. So some of the new stuff that's going on, 5G, we're talking about 5G a little bit in this talk. So this is a 100 by 100 massive MIMO system built out of USRP X310s. And this was done at Lund University in Sweden, where they were prototyping 5G technology. And so this what you see here, this is a patch antenna. Each one of those squares is an antenna element. So this is an example of using SDR to research next generation technology. Next, so deployable systems. For sort of the direction we're going is from only using SDR for research and prototyping to using the same system that you're doing the research on for actual, take it from the lab and just take it in the field and it just works. And a good example of doing this is Amarasoft's software. I'm going to show hands for people who've heard of Amarasoft. Wow, okay. Not as many as I would have anticipated. So Amarasoft is the brainchild of Fabrice Allard, who you may know from FFmpeg fame or QEMU fame. He's done a number of other things. He sort of goes silent for a year or two and then emerges with some groundbreaking technology nobody thought was possible. And so this is one of the examples. He sort of went silent, and a couple years later he came out and said, oh, by the way, I implemented an LTE base station entirely in software, and it runs on an Intel processor. This is his work. It runs entirely on GPP over Ethernet connection that works on the USRP X310. That's what he used to develop it. That's what Microsoft OEMs with their software. And this is an example of using something like that in your lab and then just taking out the field and you have an operational USRP. OEM configurations. So this company, Navsys, located in Colorado Springs, so they are using SDR for essentially they've integrated it into their own system for GNSS recording playback. And one of the things that I'll talk about in sort of the meat of my slides is that developing hardware can be very difficult. And there's a lot of ways that you can leverage SDR to sort of leapfrog a lot of the nasty stages of product development. And this is a great example of that, where they took an SDR, configured it to do exactly what it is what they wanted to do, and didn't have to do a lot of that low-level stuff. Which takes you to systems integration. Is everybody aware? Actually, so another show of hands, who's heard of the ISE E3 reboot? Yeah, this one actually got quite a bit of international press. So I don't know if you know, but what they did, and this is Paul in this picture. He has a presentation tomorrow. The picture in the top right is the Arecibo satellite in Puerto Rico, and they actually connected a USRP into the back end of that. So Arecibo is feeding directly into a USRP. And they used GNU radio. This is sort of washed out. I don't know if you can tell. That's a GNU radio for that, and it was GNU radio that reestablished communication with the ICE3, which is it's phenomenal. So this one actually is pretty recent. So I don't know if you raise show of hands for who heard of the Global Star hack, right? So this is right before Black Hat, maybe it was DEF CON. Anyway, so this hacker says, you know what, I'm giving a talk at DEF CON. I've compromised the Global Star satellite system. So he got a lot of press. This is the Register's headline about it. In typical Register fashion, you can tell they're very snarky, right? We've never been hacked, so everything's fine. It says hacked firm. So don't expect anything less from them. But this sounded really cool, right? So I saw it on my news feed, and I reading through it, and they had a picture of the device they used to hack Globalstar. So that looks familiar. That is a V200, a USRP V200. That is actually this is our low-cost product. This is the $675 product that we sell as an entry point. So I do not attend DEF CON, but I heard it was a very interesting presentation. And then lastly, SDR for education. And this is becoming more and more prevalent, where universities are moving from sort of a simulation and theory only classroom to an actual, okay, now that you've written a modem and simulated it, stick it on hardware and try it out.
I know.
So this, fair question. So I took this slide from NI's LabVIEW course, and since DT does not use LabVIEw and they use radio, you're not on this. Yeah, points. Okay, and finally, flexible development tool. So this Utah State, sponsored by L3. We're building satellite ground stations, and so what they did is they used the USRT to do the processing behind satellite dishes, but they sort of developed it in real time. So they hooked it up, and they were able to dynamically tune the radios to make things work and to correct for things they hadn't necessarily thought of during the original design. And it's a good example. This is a good example of using SDR as a tool that you can use both in the lab, and then when you actually deploy it, take advantage of its reconfigurable nature to correct and adjust for the truth of the real world. So I'm going to sort of go into the background of this. So first, what is software radio? So this is actually defined by IEEE at this point and the Wireless Innovation Forum. The definition is a radio in which some or all of the physical layer functions are software defined. My personal definition is probably a little different. I think everyone might probably have their own. At EDIS, we tend to think of software radio as from a more holistic perspective, going from the physical layer all the way to the application layer. So I'm going to use that, probably use the word software radio, not quite in that definition a few times in this presentation, but that is the industry accepted definition for software radio. But the layman's definition, right, is one device that can be used for many things, and it's tunable software. So one of the concepts that we've had here in the computer radio community for a long time is knobs and meters, right? So you build a software application, flow graph, you build a computer radio flow graph, and you have knobs which allow you to tune various components of the radio, whether it's frequency or analog bandwidth or gain, that sort of thing. And meters, things that you're observing, right? So whether that's an FFT sync or your bit error rate, and your manually or automatically making adjustments as needed. And the more sort of thorough swap out of that, right, is instead of just tuning the knobs and reading the meters, you could completely reconfigure your radio device. So a device like USRP, for example, where you have an FPGA, if you have your application loaded into the FPGA and in the middle of running something, you say, you know what, this P25 thing isn't working out. I'm going to load an LTE base station into this and completely change the functionality of the radio. These are things that everyone's doing now, and these are very possible. So a brief history. Everyone, raise your hands for people who've heard of Joe Napoleon. Okay, is Joe here yet? No? Okay. So Joe's actually giving the keynote tomorrow. It should be a fantastic keynote. So Joe actually coined the term software radio. He went on to then also coin the term cognitive radio. But he coined the term software radio in 1991. In 1998, Manual Inc. was formed, and this is actually important because there's a project called P-Spectra from MIT. And P-Spectra got incorporated by, or it was used, that code base was used as a foundation by a company called Spectrumware. And Spectrumware, and the founders of Spectrumware went on to start Manu Inc. And Manu Inc. was the first that I know of, the first commercial software radio company. And Computer Radio, when Eric Lofton started in 2001, was originally based out of this, it was built out of the same code base it came out of MIT, the P-Spectra. P-Spectra code base was originally used for Computer Radio. Computer Radio, the underlying stuff at this point has been completely rewritten. There's no P-Spectra code left in Computer Radio. But it came from the same place. So Eric Lofton started Computer Radio in 2001. 2003, Matt started working on the USRP just to scratch an itch. If you're ever up for interest in story, you should ask him why he started this. He actually never really intended to start a company and tried his hardest to get everyone else to build userts because he didn't want anything to do with it. 2008 was the first OpenBTS GSM base station demo. It was actually done on a USRP system. So show of hands, who knows OpenBTS? Okay, all right. 2011 was the first radio conference, and 2012 was the release of Microsoft's EOD software. So, in just over 20 years, we went from a coin software radio to a full LTE software stack. And now I'm going to go, for most of this presentation is going to go through how we got from that 1991 point to this 2012 point. So why is SDR so awesome? The fact is that hardware is hard. It's hard. It's slow, and by slow, I don't mean processing slow. I mean, if you've ever designed a piece of hardware, it's not like building a piece of software. And, well, these days it's not like building a piece of software. You do the hardware design, you do the schematic capture, you do the PCB layout, you have to get them built, get the boards populated, you figure out there's something wrong, and you have to spin the whole thing, and it takes another 3 months. So if you think FPGA compile times are bad, you should try making hardware. So hardware makes things difficult, and it's very expensive. In Silicon Valley, right, there's a new web startup every day, and somebody locked in their basement can crank out a new web product in a few days. Just not the case with hardware. So SDR is amazing because it sort of you can mitigate that. You have this reconfigurable device that you can use. There's not anything. So I'm obviously going to plug USRPs as an example. You don't have to make your own hardware. You can use userts, and you can configure the device for your own purposes. So it's great for experimentation and prototyping, but it's also fantastic for future-proofing. And what I mean by future-proofing is for anyone who's ever developed a radio, call them waveforms in this particular usage scenario, and then 5 years later you have to update your waveform to run on a new system, or you develop a waveform on a new system and then you're told it has to run on a legacy radio that's 15 years old and doesn't necessarily have quite the same requirements. That sort of porting can be difficult, and SDR is a really, really great way to mitigate that. Because you have your one application, and as long as you're abstracted out from the hardware, like Computer Radio allows you to do, you can take Computer Radio flow graph and move it from hardware to hardware, piece of hardware to piece of hardware. So this was the original concept that Matt had for the USRP in 2002. And actually, if you go and look up the, thank you, Mike. If you go and look up the concept drawing for P-Spectra from MIT, it doesn't look too dissimilar. But really, what you have is, on the right side, you have radio. There's some sort of data transport here at USB from your ARC front end to a computer. And then he has this box, SDR engine, which is a combination of driver, OS, that sort of thing. And then SDR app, which would be, Computer Radio, program. So what makes this all possible? We're doing our processing in software, right? And so you need something to actually do the processing. So CPUs, FPGAs, so I've sort of picked the major ones that we see most commonly. CPUs, FPGAs, GPUs, DSPs, massive multicore, which I'll talk about. I don't know, it's probably not an industry accepted term, and ASICs. So as you're developing an SDR, you have a lot of, you're going to have to decide between one or more of these, right? And each of them has its own trade-offs. So, I mean, general purpose versus specialized functional units, right? This one's pretty obvious. You compare a general purpose processor, GPP, like an Intel CPU, to something like an ASIC, right? There's the widest spectrum from general purpose to a specialized functional unit. And there's a lot of pros and cons to each. Development complexity versus app performance. So we're talking purely about software. A good example is the difference between writing Python, which is not terribly complex from a developer's perspective, and you get okay app performance, right? Versus writing assembly, where you can really get in and optimize things and get amazing application performance, but your development complexity is increased dramatically. So custom systems versus standard high volume. So what I mean by this is, so I'm going to use USRPs as an example again. Building your own custom platform or custom processor or custom radio for each application you have versus using a general purpose piece of equipment or a general purpose component and reprogramming as needed. Single purpose versus multi-purpose. So a good example of this is FPGA versus DSP. You can program FPGA to do what you want. DSP is sort of targeted to one particular area. And then finally, all of the above versus power consumption. So, I mean, the absolute best you're ever going to do in power consumption is a highly specialized ASIC. It does one thing, and it's what you need it to do, and it does it very well. You have low power consumption, but going back up through the trade-offs, you have high development complexity, it's a very custom system, and it's very single purpose. So I'm going to go through each of these and talk about each a little bit. So general purpose processors. So the key to complex, I'll say complex software radios and GPPs at this point is SIMD operations. Here's a show of hands for who's familiar with what SIMD is. Okay, all right. So SIMD is single instruction, multiple data. So think of it like doing matrix multiplies, right? Or actually, yeah, that's a good way to do it. You're optimizing. You're issuing a single multiply instruction, and you're doing many multiplies in there. So this became a big push. The industry really started pushing on this in the mid-90s because it became really clear that multimedia was going to be the big driver of technology, right? So Sun released GIS in 1994, Intel had MMX in 96, AMD made 3D Now in 1998, and subsequently Intel and AMD started suing each other into oblivion. So SIMD is really what makes this sort of thing possible. And computer radio has its own library called Volk now, which Nathan's giving a talk on. And that's a vector of optimized library kernels, yes, thank you. But Volk is the piece of computer radio that actually does SIMD stuff under the hood for you. So you can build a radio flow graph, and it's actually taking advantage of the SIMD technology under the hood if you haven't tried to find it. So GPPs, we hit the single threaded wall in 2006. And so now we're putting more and more cores into systems, and we have hyperthreading and that sort of thing. But in general, these systems have become harder and harder to program. Now you might be sort of a contentious statement, but my argument is even if it's not more difficult for you, it is more difficult for the compiler. And compilers have increasingly, we're putting more and more trust into compilers for optimizing machine architecture specific things, right? If you're doing it yourself in assembly, or you're trusting the compiler to do it. And if not, you're not taking full advantage of the capabilities of whatever your machine architecture is. So even if this that's natural progression, right? As the processors become more complex, it's more complex in building applications for them, even if you're a level abstracted from it. So these are come a long way, but in terms of actually building applications for them, it's technically more complex now than it was 15 years ago. So FPGAs. In 1998, FPGAs were not much more than fancy CPLDs. And in 2004, we had something that resembled FPGAs now, but if you wanted anything like hard multipliers, it was money. Today, you can get thousands of giga multiply accumulates on the cheap. So we've come a long way in FPGAs, and they're used very, very heavily in a lot of radio systems. There's actually an FPGA on every single user that we design. I think actually most radios have FPGAs at this point. But they sort of remain hard to program. The most optimized implementation of FPGAs is writing low-level RTL, which at this point is either mostly Verilog or VHDL. There's still component interoperability issues. Tool chains for FPGAs are rather painful. There's long compile times. Can be on the order of hours, and if you're using an enormous Vertex 7, depending on the complexity of your code, it can be on the order of days. And they're notoriously hard to debug. And sometimes you can get away with a simple FPGA application, and you don't have to connect a logic analyzer to it and figure out why the jitter of a clock is causing you to be one bit off. I'll say if you haven't had to use freeze sparing on FPGA, you haven't truly debugged it. FPGAs are awesome, but they are also hard to program. GPUs. Floating point operations are fun, and GPUs are very, very good at them. The first King Radio GPU work was in 2007, and that was different from the UMD work, right? Or was it? I don't remember. So NVIDIA's CUDA was released in 2007. Does everybody know what CUDA is? Raise your hand for CUDA. Okay, yeah. So CUDA is sort of NVIDIA's way of allowing you to write custom applications that you can then offload into an NVIDIA GPU. Apple released OpenCL in 2009. Yes, I realize OpenCL is not targeted specifically at GPUs. It can be used on all sorts of processors, but it's used very, very heavily in the GPU world. And in 2011 was the first presentation at the very first GRCon of GPU, or offloading GPUs from a big radio flow graph, which I did not put on here. So GPUs are great at floating point operations. They have amazing bandwidth. The problem is that there's horrible latency. The overhead to actually offload an application into a GPU is long. And I obviously don't mean seconds long, but if you're building a radio system and you need millisecond or microsecond level latency, it's going to take an order of magnitude longer than that to stick something in a GPU. So my analogy here is kind of like shipping a hard disk, right? You get amazing bandwidth but horrible latency. You take a 10 terabyte hard disk and overnight it to a friend, and you ship a lot of data a lot of data all at once, but it took a long time to get there. And they're still hard to program. Programmable DSPs. So 1996, they were good at fixed point only for the most part. You could do some FIRs, IARs, about 20 minutes. Today, we've come a long way. I'll say that I think DSPs are becoming less and less common. So by DSPs, I don't mean like the DSP slice in an FPGA. I mean an individual die is a DSP, like a TI C64 or something. They're becoming less and less common in general purpose software radios. But they are still very, very widely used. And they've come a long way with many, many programmable sections. And now, instead of being fixed point only, we're talking about 80 gigaflops. But they are also harder to program than they used to be. Massively multi-core. So what I mean by this are numerous efforts to create dies that have hundreds or thousands of processing cores on them. So examples of this, Sandbridge, Coherent Logics was one. Coherent was actually at the Wireless Innovations Forum for many, many years. PicoChip, Tylera, and a few others. In general, they're proprietary. Intel has jumped into this game 5 or 6 years ago, and they named their product the Intel Xeon Phi. And their goal is to use x86 instructions for these massively multi-core machine architectures. What they sort of ended up with is something that looks a lot like a GPU that's programmed with x86 instructions. So this is competing directly with things like NVIDIA's Tesla systems. So it's there, it's available. I've never seen a software radio built out of one. It has the same, right now it has the same sort of limitations that GPUs do. Okay, so hardware challenges. Hardware's obviously come a long way. But so when Matt started designing USRPs in 2003, his goal has always been to do DC to 6 gigahertz in one product. And the way he achieved that at the time was by this sort of plug and play daughter board idea where daughter boards covered for frequency bands, because the fact of the matter was there were not wideband synthesizers that could synthesize frequencies in that range. They would have had to increase complexity dramatically by adding doublers and dividers and all kinds of different channels and bands and that sort of thing. And we've come a really long way. So we actually just recently, beginning of this year, released our first product that does 10 megahertz to 6 gigahertz. Digitally, you can get down lower. So we've sort of finally achieved our DC to daylight goal. But the fact of the matter is that in terms of hardware, wideband flexible components are still one of the primary limitations. So as an example, there's about 35 FTD and TDD LTE bands worldwide. So if a hardware vendor was able to make a filter, one filter that would work at all 35 of those bands, right? It's the one ring to rule them all, right? They could sell that filter to every device, every LTE device in the world, and charge and have a significant upsell, because as a hardware vendor or a hardware designer, you don't have to use one filter instead of multiple. You don't have to design one chain in your RF path instead of multiple. So a lot of people try to do this electrically and mechanically, and it just hasn't panned out. It's poor linearity, high loss, low reliability, and they still remain incredibly expensive. So this is an example using filters. It's the same no matter what you do. We're talking about ECO PLLs, we're talking about balance, amplifiers. Getting the sort of performance you need in wideband components remains very challenging. And in general, the more flexible it is, the more power it is. And I don't mean this, it sort of applies at the system level, but here I'm talking more specifically at the component level. It applies for everything from amplifier, that's a single RF amplifier, all the way up to what we were talking about before in terms of processing platforms. The more flexible it is, the more power hungry it is. How am I doing on time? Okay. So this is sort of a generalized use of architecture. I'm going to skip this and kind of go to a new development that we've seen in recent years, which is all-in-one RFIC, which is more or less an entire radio on one chip. So Motorola sort of kicked this off in 2007. We had a few at Virginia Tech at one point. I never saw them outside of that, but they designed this chip. It was 100 megahertz, 4 gigahertz, I actually don't remember the name of it. Yeah, it was used here and there, but it never really took off. The Line Microsystems released the LMS 6002, which has been used on a number of commercial SCR products, including several that were Kickstarter. And I think Tim Newman will probably go through a couple of these in his presentation later today. And then we sort of hit our current grandmaster, which is the analog devices 9361, which is 70 megahertz to 6 gigahertz, 2x2 MIMO, up to 61.44 megasamples per second. on one chip. And the one chip is, the size of, slightly larger than a synthesizer. It's effectively an entire software radio on one die, including ADCs, DMX, gain chains, everything else. And these are really revolutionizing hardware design for software radio at this point. Antennas and filters. So anyone who's actually operating real-world nodes, it's not unusual to need to do something like this, where there's a minus 110 dBm signal, and you have 0 dBm interference, and somehow you can get that out. So good filters are the magic here. It doesn't matter if you're doing direct conversion or superhead radios. Tunable wideband filters are the holy grail. They don't really exist yet in affordable prices. And there are tunable antennas now that are being researched and talked about. We're moving to the final phase of my talk here. So what hasn't happened yet? We've come a long way, right? In terms of processing platforms, hardware capabilities. We went from enormous radios down to software radios on one die. So dynamic spectrum access, which we've been talking about for years, in the real world hasn't really come to pass yet. Now, my disclaimer here is that it looks like it is happening in the near future. The Citizens Broadband Radio, this is a 3.5 gigahertz band, and the ADVS3, which the SEC is currently working on. And a number of the companies that are trying to address these areas are doing it with dynamic spectrum access. But we haven't really seen it yet. Interoperability remains a serious problem. As anyone who's worked in the public safety sector knows, trying to get all of the systems to talk to each other, even though many of them are SDRs at this point, remains a significant challenge. Easy heterogeneous processing. So what I mean by heterogeneous processing here is going back to that list of processor types that we went through, right? GPP, GPU, FPGA, DSP. The ability to write an application workflow graph that seamlessly allows you to intelligently or unintelligently offload processing between all of those is still somewhat elusive. But I will say, and lastly, better tool chains. I'm mostly griping about FPGA compilers here, but I will say we're actually trying to address this at EDIS with RF NOC. There'll be a talk later this week about RF NOC, and there's a tutorial session on it. It's something we're really excited about. But our goal, one of the things we're trying to address now is not just hardware, but also trying to fix this issue of making this massive amount of processing power that we now have available actually accessible. All right, so what's driving hardware requirements? So 5G is a big one. We've been talking about 5G a lot in the last year or two. I sort of threw up what I consider to be the four main hardware requirements for 5G. 5G is sort of undefined. Not that 4G is defined, but 5G is really undefined, right? It could turn out to be anything. When I say 5G, what I'm talking about is small cells, either centimeter wave or millimeter wave, massive MIMO, and fast PHY switching. And in terms of designing hardware, these are the major hardware requirements that are pushing technology for us. And SDR, I want to point out, SDR already is the development platform for 5G. It already is being used. National Instruments and Nokia demoed 10 gigabit per second link operating at 73 gigahertz at the Brooklyn 5G conference at NYU Poly this year. And that was all done in SDR. It was all SDR. Machine to machine. So this is a quote I took from the Wireless Symposium at Virginia Tech from this year. You've never been to that conference, by the way. It's a fantastic conference. But the primary customer of next generation communication systems won't be people, it will be machines. Now that sounds a little ominous. But there's a lot of truth to that, right? And I think a lot of the things we've been talking about in terms of we used to call it smart radio, we're talking about cognitive radio. Paul's presentation, really talked about a lot of things like this. In defense world, we talked about spectrum agile radios and that sort of thing. I think taking the human out of the loop places a lot of requirements not only in the hardware but also in the processing and the applications that you guys are writing. And that's going to continue to drive stuff. Ubiquitous radios. So this also sounds a little scary at first. I don't. It's but really what I mean is, more things with more radios, and that it's everything. And I mean that from your tire pressure sensor in your car, which is a radio, to the fact that your cell phone has like 8 radios in it, right? We're going to get to the point where just about everything has some sort of wireless communication capability. And that is really driven, the ability to do that is driven entirely by hardware. And more localized processing is finally becoming feasible, which is important for things like sensor networks and smart meters. So it used to be if you were designing a software radio, designing a software radio, and let's say you were designing a sensor network, for example, you would collect whatever data was important to you and ship it over some sort of wireless backhaul to somewhere that was actually doing important processing, right? Because it was it was very, very difficult to do processing locally, because you're either designing an expensive ASIC, which takes a tremendous amount of engineering time, or you're doing it at somewhere easier like code. But now we have things like the Xilinx Zinc chip. Can I show of hands people who are familiar with the Zinc chip? Okay, so the Zinc is it's FPGA programmable logic and 2 hard ARM cores and 1 die. Right, so you can write an FPGA application and move data back and forth between ARMs all on one chip. And so it makes it much, much easier to do localized processing. So now instead of building dumb nodes that you're just deploying that collect data and ship something off where you can actually, whether you're doing sort of data massaging or you're actually doing some local processing and just sending what's important back over the backhaul. That's possible now. And I do want to say that open source, especially in radio, but open source in general, I think we're going to continue to see a tremendous amount of growth and importance. So I have 2 examples here that sort of show that they're signs of what's to come, right? First of all, Microsoft open sourcing anything is amazing. Microsoft open sourcing .NET is huge, right? And Red Hawk, which was open source by the government sponsors, is also a really, really big deal. And so if you ever had doubts about where open source is going, I feel like it's pretty clear at this point. In terms of software, we still, like I said earlier, we need to make the massive processing capabilities that we have available now easily accessible. And we have GPUs, we have FPGAs, we have all of these items, but they're difficult to use. They're difficult to incorporate in your system, they're difficult to program. I think we're going to continue to see a shift of key applications functionality from hardware to software, right? And so software radios follow the same trend that consumer computers did, right? It used to be everything was defined in hardware, and now what's important is what's in your web app. And not that good radios will start making web apps, but you hopefully see the parallel. And finally, software use for both prototyping and deployment. What I mean by this is sort of going back to my examples before of like the MRSoft LTE stack, where in the early days of software radio, you would see, okay, well, I'll use software for my simulation and my prototyping and proving out my device concept. And then, that's not what we actually put in the field. We sort of take that, we prove it out in MATLAB or C++ or whatever it is we're using, and then we build our specialized ASIC with different code, and that's what we're sticking in the field. And getting to the point where you're using the same tools and the same hardware for both your prototyping and your field performance. I think everyone's lives easier. I think that's the direction we're going. I think Green Radio is doing that. So that's all I had. I think I used the entire time block. I don't know if we have time for questions.
First, let's take a minute. At the risk of going long into lunch, are there any maybe like 1 or 2 quick questions?
Yes, hi. You mentioned about the performance penalty going between FPGA.
I'm sorry, I can't hear.
Yes. I'm talking about if there is a processor and let's say a GPU. You mentioned about the parity of going between the two.
Yeah.
It's moving data. Isn't that also a problem if there is, let's say, you mentioned about an embedded core, Zinc, and an FPGA? I think there is also a problem if you're trying to move data between the Zinc and FPGA.
Yes, you're right.
That's the same problem, and yeah, on the same note, we have like OpenACC, which is the directive-based approach, to ease out, things in GPUs. Talk about that.
Yeah, sure. So going in here, he was mentioning, I talked about the overhead and offloading processing from a GPP to a GPU. And there's sort of a parallel in things like the Zinc, where you have programmable logic on the same die, as ARM cores, because you still have to move data between these sort of two fundamentally different processing platforms, right? And so what I'll say is, yes, there's still something of a fence there. I mean, you can, on the Zinc, the fact of the matter is if you sit down and spend time doing it, you can write a highly optimized DMA engine that could you can move more data between the programmable logic and the ARMs on the Zinc than the ARMs are capable of processing. So and that takes work. I'm not gonna say if you buy a Zinc eval board and turn it on, and I got 200 megabytes per second of transfer between the two. But I think you can move data quicker than you're capable of processing it on the ARMs. That said, I think your question was more general in that how do we make that better, or how do we do that faster? And
I said with OpenACC, like to ease out the GPU development. I think, and I'm just trying to compare that to our account, that goes.
Okay. So I'm not familiar with the project that you mentioned.
OpenACC is the standard to just you can annotate, just put some directory and the code gets compiled.
Okay, let's talk afterwards. I'm not terribly familiar with that. Yeah.
So I love your slide on the open source and where it's going and it's the right direction and everything. And I hope you don't mind if I give another example on that. So at last FOSDEM, Raymond Knopf from OAI and Paul Sutton from Trinity gave presentations on where free software is going and what role it's playing specifically in communications and cellular communications. And I recommend, if you're interested in that kind of thing, I recommend checking out those talks because they're available online, through the GNU Radio website or the FOSDEM websites.
All right, and if you'll allow me 30 seconds to philosophize. I think this is important, especially at an intro day. What Ben pointed out, he has a lot of questions. Who knows this, who knows that? And different parts of the crowd raise their hands for different things. But I think that is an important lesson for what software radio means. It's the whole stack, right? It's from the RF world all the way up to the operating system and then the software engineering design, the mathematics, the comms theory. All of that is part of the software radio world, which is intimidating for a lot of people who are focused on, kind of were raised through one kind of silo of education or use cases of comms. But that is an important factor in our world. Now, it doesn't mean you have to become an expert in all these things. But through a presentation like Ben's, where we're talking about this is software radio, there's a huge number of aspects to this that come into play. So keeping familiar with it, right? Keeping up with the technology. It's a hard thing. We find it fun. I think that's why we're doing this. But it's something to recognize. I think it's just, that's my point here, as people coming into this world, it is a thing that has to be recognized and understood. So we'll think about it in a second. We're breaking for lunch now. 12:30, we're gonna start up again. And remember, we're splitting between the tutorials over there, just right next to us. We're coming back to the main sessions here. There are 16 seats. It's gonna be first come, first serve. 16 seats over there. I believe there is more room though, so if you have your laptop and a hardware device, a USERP, it's going to receive only, so a USERP, RTL dongle, so if you bring your own hardware and there's space, I think you can kind of pack it a little bit in the back, but do be aware that it is first come, first serve when we start again at 12:30.